Welcome to lecture 14. We'll quickly run through the semantics of the while programming language and then go on to what complicates matters. So this is the syntax of the while programming language. The most important things are that it consists of imperative commands which change some notion of state. I defined a state as in a simplified form as a variable value mapping. Sigma is the set of all states. We'll assume an infinite set of variables available to us. Expressions are evaluated in a state. Commands are state transformers. Yeah.
We define environment also as variable value binding, and we are defining state also. So how are they different?
That's right. That's a question we'll address at the end of this lecture. So we looked at state changes. So given two states, I defined a state updation in which really corresponds to having a single assignment statement. This updation could be changed, could be generalized to also multiple assignment, but maybe we'll worry about that later. Okay. So in the expression language, what I said was that at this state, at least, there seems to be no real difference between environment and state, except, so in the expression language at least there's no significant difference. So you have the same kind of rules, the evaluation of, starting with the evaluation of identifiers in a state, and the normal rules for expression evaluation, which are strictly left to right sequential evaluations. And then we, since our while language also contains Boolean expressions, we required a semantics of Boolean expressions. In a general programming language, Boolean expressions would be treated on par with the normal expressions. There's only a type difference in the sense that you would allow Boolean variables and assignments to them, and whatever you can do with integer expressions, similarly you can do with Boolean expressions too. However, in the case of this particular language, since it's a sort of greatly simplified language and we did not allow Boolean variables and we did not allow any other kind of the Boolean expressions were used only as a via media between, in order to construct commands, conditional commands, right? So this has this following semantics, but even when the Boolean expressions are an integral part of the expression language, you wouldn't, the semantics would not change too much. Okay, except that one would have to look at the type distinctions between the various kinds of variables, and one would have to do something about types, and that's a matter we'll get into after some time. So here again we defined the evaluation of Boolean expressions in a left to right manner with of particular interest is this unary operator, which we did not encounter in the expression language. The Boolean expression language actually assumes the existence of a Boolean algebra and a semantics as defined by a Boolean algebra for Boolean expressions. So for example, you have that true and that the ground values t and f are not identical, and unless you specify clearly that they are not identical, you could have a one element Boolean algebra and all the properties of Boolean algebras could be satisfied. So and the fact that they are not identical and they are actually complements of each other is given by these two rules, these two axioms, B1 and B1 prime, right? So, and of course we had to relate Then we have these usual Boolean operations, which essentially show a complete left to right evaluation. B4 indicates, for example, so if you have a general Boolean expression of the form B1 or B2, then you would repeatedly apply B3, which means you would be evaluating the left operand till it reaches a truth value, and then you would start evaluating the right operand. So it shows the left to right evaluation, and of course it always satisfies the standard truth table for a Boolean operation. Yeah, which is so everything is subject to the existence of such a model of meaning in the Boolean expressions. And since our Boolean expressions acted as some sort of intermediate stage between the expression language and the command language, we have to relate the Boolean expressions also to the derivations in the expression language, and of which we had only a simple operation, a simple relation, the equality relation on expressions. So the rules B6 and B7 also show that, also give you a left to right evaluation of the equality. You would apply B6 several times, which means you would evaluate the left operand of the equality till it converges to some integer value, and then you would evaluate the right operand and use till that also converges to some value, and you would check the equality of these two based on the fact that m and n, since they are there in the underlying machine as patterns, if they are identical as patterns, then it would be true, otherwise it would be false. Right. Right. So as I said, I mean, we don't need to go through this whole thing. We could, for example, abstract away from the intermediate stages and simply give a fairly non-deterministic rule which says that if E1 can evaluate in a finite number of steps, this star indicates a finite number of steps, 0 or more, to some integer value, and E2 can be evaluated in a finite number of steps to n, then this can be concluded depending upon these patterns m and n as given by this, right? So, and then this rule has a nice property that it does a further abstraction from the order of evaluation in the transition system, so on and so forth. And you could modify these Boolean expression evaluations. For example, you could have a strict right to left order of evaluation if you liked, or you could have a partial evaluation. You could give rules for partial evaluation, especially the OR operation, for example, or any other binary operation. You could give rules for partial evaluation. In particular, if the left operand, for example, evaluated to the truth value t, then you can have in a single transition the entire Boolean operation could go to t, right? So that you don't have to evaluate the right operand of the OR, right? So, and you could also do parallel evaluation. You could do parallel partial evaluation. So there are many variations depending on how you want to specify the language, right? So then we came to the most important thing, and that is commands. And I defined this set of configurations. As I said, commands change states, and the first rule of the command itself tells you one thing, that there's one important difference between states and environments, and that is that in an environment you can have a redeclaration. I mean, the whatever modifications you make are redeclarations, okay, redefinitions of given identifiers. And however, if you remember what we said about declarations, is that the little environments that declarations create are only intermediate stages in a larger computation. A declaration does not stand by itself. An expression stands by itself, especially in a functional language. The expression is evaluated in an environment, and in the process of its evaluation, little environments are created and destroyed. So the evaluation of the expression from start to finish goes through some intermediate stages of the creation of new environments, in which there might be redefinition of identifiers. But the whole point is those changes in the environment are reversible, in the sense that whatever gets declared also goes out at the end. In the case of states, we are talking about capturing a general notion of an irreversible change in, say, the value of the identifier, right? So conceptually, even if symbolically it didn't look too different, conceptually at least there is an important difference which we have to capture somehow. Okay, and one of the reasons why we'll introduce stores is to capture this conceptual difference between environments and states, right? So the assignment statement is an example of a change that is irreversible. For example, if you have a large command evaluated in a state so if you have some command which is going to be evaluated in some starting from some initial state sigma. So let's have some large command, maybe with some assignment here, and I don't know, something else. Okay, when this is evaluated in a state sigma, starting from a state sigma naught, at the end of this you get a new state sigma 1, which is different from sigma naught in the sense that x now has the value which is one more than the x given by sigma naught. Right, and this state change is irreversible in the sense that it's starting from this state that further state changes take place as you execute the command, and you finally end up with some final state, let's say sigma f, at the end of this command. Right? In the case of an environment, what you could have had inside were declarations which created little environments, but at the end of it you still had the original environment with the same name value bindings that you started off with. So the environment rho naught and the final environment rho f were the same. There was no difference. In this case of state change, so in that sense all the changes that occurred inside in the evaluation of an expression were all reversible. Whereas in the case of state changes, and in general in an imperative language, we are looking at some concept which allows for irreversible changes to be made. Here the sigma f need not be the same as sigma naught. Sigma f may not be the same as sigma naught even for the value x, unless an equal amount of work was done to get x back to its original value in sigma naught. So even if your command had been such that it restored all values back to the original and your sigma f was the same as sigma naught, those changes were irreversible in the sense that the amount of effort required to make those undo the initial changes that you made was as much as the amount of effort you required to make the changes in the first place. Whereas in the case of environments, there's something automatic about the way the new environments that are created get destroyed at the end. Right? So there is something conceptually different between states and environments. Right? And this is something we should capture. So as a notion as abstract as state does not really capture that notion as we capture this difference totally, but it does capture to this extent, in the sense that you can see from the semantics that state changes occur, and and the final state need not be the same as the initial state. So yeah.
Then what is the store?
We'll come to the notion of a store soon, right? We'll come to the notion of a store. But let me first go through this while language. So I showed a sequential evaluation of the sequential composition operation, semicolon, and so this means that you evaluate the left operand of the semicolon till it reduces to having made just a state change and there is nothing more left of that command. So commands are something that get consumed and get reflected as state changes, and then you start evaluating the right operand. Okay, you could evaluate the right operand, and in the case of the conditional, you evaluate the Boolean expression and you transfer control. The transfer of control is like as getting rid of one arm of the conditional depending upon the truth value of the Boolean. And lastly, we had this the while loop, and of course there is something about this while loop which is not quite correct. I mean, which does not quite meet with the philosophy we started out with. What is that?
After the execution of the while loop, the state doesn't change. Like, so
It does change. It does change. If you were to,
so C6.
yeah, C6 says that this is equivalent to, I mean, this moves in one step to a program which has this form, and the sequential composition rules tell you that there could be state changes. For example, you have some C1 semicolon C2, which is really what the C semicolon while we do C is like. So this is C1 and this is your C2, and C1 could create state changes and could finally terminate, and then you would evaluate C2 in this new state, sigma prime. Right? So it's not as if there are no state changes. But there's something else that is seriously wrong with this while loop. It conforms to our intuition about how while loops are executed, but it does not conform to some other aspect of our semantics, our notion of semantics. What is the most important feature about semantics, syntax directed translation, recursive descent parsing? What is common to all this? What is common to all these definitions? So this is something that this is what you get by gut feeling after having programmed enough in a while sort of language. But there is something wrong with it. And what is that?
The final expression is even more complicated than what we were trying to
Absolutely. He says the final expression is even more complicated than the initial expression you started out with, which means that this definition is not inductive. Several applications of this might only give you more and more complicated things. It's like, well, it's like what's wrong with this recursive definition? Let's take a function on numbers. F of n is 0 if n equals 0. Otherwise it is f of n plus 1 minus 1. What's wrong with this definition? So what's wrong with it mathematically and what's wrong with it computationally?
It's infinite.
Can go. Yeah, and mathematically there is no inductive basis to.
Mathematically it's just an equation which has to be solved for and there is a solution too. I mean, the solution is f of n equals n is a solution to this equation as a mathematical equation. What is wrong with it is not mathematically. What is wrong with it is computationally, in the sense that it is not inductive. Right? And this semantics of the while suffers from the same problem. The semantics of the while suffers from the same. For example, this semantics, if you take C6 and C7, then what it means is that in any state, while B do C is equivalent to, if you take a combination of C6 and C7, is equivalent to if B, then I'll use begin and end, okay, because I require to bracket. Begin C semicolon while B do C. Yeah. So C6 and C7 are mathematically quite meaningful in the sense that all that they say is that this is equivalent to this. Okay. If you had a no operation in your language, I mean, you could also write this as else skip, let's say. A skip is a no op. Anyway, so it just gives you an equation. It does not, and which is perfectly meaningful, and which is why implementations actually work this way. It's perfectly meaningful, but however it's not inductive. Precisely because the resulting expression is much more complex structurally than the original expression. Right? But the fact that while loops are executed and they give you meaningful results means that there must be a way of giving a semantics which is inductive. Anyway, I'll let you think about it. There is a very simple solution to make it inductive. Just like there is a very simple solution to make this to make this computationally more meaningful. right? You could either just give this non-recursive definition, or you could even give a recursive definition which is computationally more meaningful. So there is a very simple solution which I will not go into now. Anyway, this is what this is what your gut feeling says should be the semantics of the while loop, except that it's not inductive, right? So anyway, so what this has led to is something that I mentioned previously, is that an important semantical notion which should come out as part of your operational semantics or any kind of semantics is program equivalence. All right. So let's look at program equivalence in the context of this language, and I would say that we'll start with expressions. Two expressions are equivalent if and only if for every state sigma in which they are both evaluated, they yield the same values. There ought to be something else which right. So so I can define a function which denotes evaluation. So I can define a function I can define a function, if you like, eval of E sigma. There is no reason, unless you have explicitly proved it, there is no reason to believe that evaluating an expression gives you a single answer, right? Till you have proved that until you have proved it, you cannot be sure. So we'll define eval of E sigma as being equal to the set of all values m which so we'll just look upon this as a set of all values that eventually lead to a terminal configuration. Right? So in the expression language, terminal configurations are of this kind. So we'll just think of so if, for example, an expression evaluation, until you have proved it, you don't know whether expression evaluation actually terminates. Do all expression evaluations terminate? This is something that you have to prove. Supposing you haven't proved it, then you cannot assume that expression evaluations do terminate, in which case this set would be empty. Right? So, or there might be some evaluations of this expression which might terminate, some evaluations which may not terminate, in which case let's just, for simplicity, assume that the evaluation of this expression consists of just the set of set of values which are reached on termination, which is not quite correct. Okay, but for the present, let's live with that. Or we could also introduce a new fictitious element called some undefined or something which represents non-termination, and we could define the set as the set of all possible evaluations which yield proper values and yield an undefined value. Then whatever may be your definition of this eval, we of course have to consider only a finite number of steps in the evaluation, right? So we would say that two expressions are semantically equivalent provided in all states, in all possible states, the evaluations of these two expressions yield identical sets of values, right? Similarly, in the previous model of a functional programming language with environments and so on and so forth, we could think of it as evaluating these expressions in all possible environments. So we would say that two expressions are equivalent only if in all possible environments in which they are evaluated, they yield the same set of values, right? And the same holds with Boolean expressions. And when are two programs equivalent, I'll define the notion of an execution, in which I will say that given in our case, in our simplified programming language, a command is also a program, so there's no distinction really. I can define this function called executions, and I can define it as the set of all final states. Right? So I can define this concept of an execution of a command or a program in our case, and I would say that, so I will also call this a behavior. So a behavior is a general word. So the behavior of an expression is just the set of all possible values it can yield, which is what our definition of eval does. And the behavior of a command is just the set of all possible final states that it can yield given an initial state. Right? And when are two programs equivalent? Only when for every initial state in which you start executing these two programs, C1 and C2, they yield the same final states or the same set of final states. Again, in this case, you do not know unless you have proved it that the program will actually, for a given input state, will actually yield only one output state. There are non-deterministic languages which do not necessarily satisfy the functionality, state to state functionality. Okay, right. So our semantics actually gives us a way of defining program equivalence, and what does program equivalence finally work out to? What does Boolean expression equivalence finally work out to? It works out to just all the laws of Boolean algebra. What does program equivalence work out to? Program equivalence just works out to equality as functions. So if you consider a program as a transformation from the set of all states, so if you can think of functions of the form right, this is the power set of states. Note that we have not yet proved that a program would give only a unique final state. It could give several possible final states. So typically, if you want to regard a program as a function, then you have to regard it as a function from states to the power set of states. Okay, so when are two programs equivalent? They are equivalent if they represent the same function, and if so, it should be possible to use the semantics to reduce it to two functions. So given two programs C1 and C2, they represent corresponding functions F1 and F2, and then it should be possible, if they are both, if C1 and C2 are equivalent, it should be possible somehow to prove that F1 is the same function as F2. Right? So one initial promise that I made of being able to define program equivalence and behaviors and so on is essentially fulfilled by these definitions. And what we'll do is you can generalize this as we go along. In each case, you can define behavior in such a fashion that it represents some functions. It does not make much sense to really talk about the behavior of a declaration, but we could define similar notions for declarations. We can talk about two declarations being equivalent, except that there is there's one problem associated with that. What's that? What's that? What happens in the case of a declaration? A new environment is built. What is that new environment? It's some name value bindings. So, supposing I decide that the behavior of, in analogy to whatever we have done, the behavior of a declaration is just the new environment it creates, or the set of new environments it creates when it reaches a terminal configuration. Then I go further and say that two declarations are equivalent, semantically equivalent, if and only if they create the same new environment. Okay? Now declarations might occur within expressions. Okay? One reason why we had to declare behavior, why we had to talk about the behavior of expressions, is because our programs cannot be semantically equivalent till we have actually defined an adequate notion of equivalence of expressions. Since our commands depend upon expressions, you have to define a notion of equivalence, semantic equivalence in the case of expressions. And so what is it that can happen in the case of program equivalence, or in the case of expression equivalence? What is inadequate about this notion of declaration equivalence?
They might bring about different changes in store.
No, we are not talking about store. Just assume an expression language with declarations like we've already done. So I define the same thing. Two expressions are equivalent if and only if under all environments they yield the same values, right? So let's look at this. Right? Now I define two declarations to be equivalent if and only if they yield the same environment.
So the environment in which they are initially declared might be different.
So okay, fine. So what I'll say is that two declarations are equivalent. So supposing I define declaration equivalence as two declarations D1 and D2 are equivalent if and only if for all initial environments rho, let me call this a new function called elaboration. We usually talk about elaborating a declaration in an environment, right? So we could say that two declarations are equivalent if and where, of course, this function elaboration, elab of d rho is defined as the set of all little environments rho prime such that in the environment row, if D is elaborated, then in a finite number of steps gives you a new environment row plan. And of course, since I'm forced to use this set because we have not actually yet proved, but it can be proved that an elaboration, at least with the syntax and the semantics that we have given, will give you a unique new environment row prime. So with this definition of elaboration, I can define this, but while this might be correct, it is somehow not adequate.
So, it may be because environments created are temporary. They are reversible changes.
That is true, but that doesn't really affect expression equivalence.
So the declarations in themselves may contain the expressions and the expressions may not be equivalent.
No. Expression equivalence means, well, expression equivalence means expression equivalence. That's it. I mean, what does expression equivalence finally boil down to? Whatever you know about the mathematical theory of those expressions. So if you're talking about expression equality in something like number theory, then which means that two expressions will be equivalent only if the corresponding their equivalence can somehow be justified by number theory eventually, because when you evaluate you get these numbers, or at least you get expressions on numbers on pure ground terms, and you should be able to prove that those two numbers are the same, and for that you will just be using pure mathematics and no programming. Okay, but there is something, while this is perfectly correct,
Two declarations when declared in different environments and they lead to,
but we are considering the equality in the same environment. This universal quantifier says that you elaborate them both in the same environment, and if you get for all possible such same environments, if those elaborations give you identical new environments, then they are equal. But what I am saying is this definition is somewhat weak. It's not incorrect in the sense that you can't give a counterexample to it, but it's weak in the sense that it doesn't really get us very far. Why is that? Why is that? I mean, what I mean is, two expressions can be equivalent even if the declarations inside them are not equivalent. In that sense, it's weak. Two expressions could work out to be equivalent, but the declarations inside them could be completely different. They might create completely different environments, and that's what happens in most cases. I mean, for example, even if the declarations look identical, they could still differ up to name changes. I could uniformly replace names in one declaration to give me another declaration, and by this definition, the two declarations will not be equivalent. I just do name changes, and this is equivalent to saying that when I have to submit my assignment, I take his program, uniformly replace all the names, I draw up a table of names, and I give corresponding different names, and all my declarations are different. Okay? But the two programs are still equivalent. And the reason the two programs are still equivalent, if I have made uniform name changes, is really because those names don't matter. part of the reversible changes which are very, very intermediate. Okay, so talking about the equivalence of declarations, and moreover, a declaration is meant to perform various kinds of abstractions, which are, well, I mean, somebody might use less number of variables and more complicated expressions. Somebody might be able to deal with only very simple expressions, so uses more declarations. So declarations could be different in various ways, and the expressions could still be equivalent. So the equality of expressions does not necessarily depend upon the equivalence of declarations. And these name changes are always done. I mean, it's a thriving industry, especially in IIT, right? So these kinds of that is one of the reasons why I'm not too bothered about the equivalence of declarations. Or at least I should have a more sophisticated definition of equivalence to really worry about it, though it can be done. Yeah, right. So there are other important questions with regard to whatever we have said about our semantics. We have to worry about when configurations get stuck. And what is a stuck configuration? A stuck configuration is one in which it's not a terminal configuration, it's a non-terminal configuration from which there is no movement. Then you would say a configuration is stuck. Then, of course, there was this problem of the inductiveness of whether all our definitions are inductive, and the while loop definition was certainly not inductive. So one way of avoiding stuck configurations was that if you make all your definitions inductive, see, if your definitions are not all inductive, then you do not know whether you have taken care of all the possible syntactical constructions. If your definitions follow the syntax, at least you are sure that you have taken care of all possible syntax constructions. So at the level of a context-free grammar, at least you are sure that you have taken care of all possible cases. If your definitions are not inductive, then there is this problem that there might be certain syntactical constructions which you have not taken care of, and you have to explicitly prove that you have taken care of all possible syntactical constructions. And if your definitions are not inductive, you cannot even use induction in order to prove it. You will have to prove it by some other complicated means. Right? Now, can there be stuck configurations even if all definitions are inductive? I'll let you think about that. But in the meanwhile, let's talk about stores. Yeah. So now it's clear that the environment and the state are really two different concepts, and they try to capture two different things. And state is a very abstract concept, which and we have tried to model the assignment commands, where we'll consider the right hand side of the assignment to be a source and the left hand side to be a target. But the thing is that our assignment commands are very simple. For example, they did not allow side effects, and when you talk about a side effect, it's equivalent to some kind of an invisible assignment taking place somewhere without your knowledge. Right? It is at least invisible within outside some scope. Right? Secondly, so even if we take our working definition as a store being an association of identifiers and values, what happens when you have these complicated kinds of targets of assignments? Right? I can have, for example, an array which indexes into another array, and I can update one array element in some complicated fashion through an indexing mechanism. I can have pointers. So my targets are not necessarily just simple variables. They are not just identifiers. they are actually complicated expressions, because the identifier P has some meaning, and this is like an operation on P. The identifier A has some meaning, I has some meaning, J has some meaning, and this is some complicated ternary operation on A, I, and J. So our targets are not necessarily just identifiers, they are actually expressions. Right? So then there are further complications. What about when identifiers get redeclared? Can you just talk about a store as such an association? Is a redeclared identifier different from the identifier that was previously there? What about scope issues? Right? And and also not all target expressions might be meaningful. So there is a separate subset of the expression language which targets can be. Not all source expressions can be meaningful. There is a separate language of source expressions, sublanguage. So in the whole language of expressions, you can actually divide it into, well, not really divide it, because they're not two disjoint sets. There are two subsets of target expression, valid target expressions, valid source expressions, and they are not disjoint. Then you also have anonymous targets. So for example, if you had such a loop, every time you create a new P, you're creating a new anonymous target. Actually, you're creating a target which has some meaning. If you look upon this as a name, it has a meaning there. But then, the next time you come around the loop, the previous invocation is anonymous. It has no name. How are you going to look at the previous invocation? Right? So your environments themselves are not sufficient to worry about it, and our abstract notion of state is also not sufficient to look at complicated programming language behaviors. Right? And further, when you have recursion, you have the same identifier, the same name for several different logically distinct identifiers which have got nothing to do with scope. So there are all these, and then you have several different names for the same object when you have something like a call by value, or a call when you have a call by reference, when you have the var parameter declaration in languages. I can do pointer assignments so that several different identifiers actually refer to the same object. And with anonymous things, with recursion I can have several different objects having the same name. Right? So these kinds of things mean that we have to refine our notion of state to something that's more tenable. Right? And so we'll come out with the notion of a store in response to the fact that a simple state-based looking upon states as just identifier value bindings is simply not sufficient to account for most behaviors in real programming languages. So we'll define the notion of stores and then integrate that with the notion of environments.